Hello, welcome to this short video in which I am going to give hints for solutions to week 3 assignment. So, this is a short video in which we are going to give hints for each of these questions. So, let us look at the first question here. The first question is an LTI system with transfer function h of s which is rational and real valued coefficients are given, and the input is a sin omega t plus theta, and what is the output. So, this is the question and you are given the 4 choices. The first, the important point to notice here is h of s is a rational transfer function, which means that h of s is of the form b of s over a of s, where b of s and a of s are polynomials in S, and the other property that is stated is the coefficients are real valued, and then the input given is a sin omega t plus theta, and you are asked to find out what the output is going to be. So, this is one of the very first concepts that has been explained in unit 10 week 3 Fourier series 1. So, in that lecture Professor V. G. K. Murthy gives you explanations on how to do this, and what you need to do is you need to write a sin omega t plus theta in complex form, and then use the fact that e power j omega t plus theta is an eigen function or an eigen signal to a system with rational transfer function LTI system, and then express the output in terms of input times a complex constant. The other thing that you need to use is the fact that the system has real valued coefficients, which means that the frequency response has certain properties, namely the magnitude response is even and the phase response is odd. Using that fact and the fact that the input consists of 2 complex eigen signals, you will be able to get the output for each of these complex exponentials and then combine them and get the final form. So, this is the way you need to proceed with question number 1. Now, let us move on to question 2. Question 2, you are given a circuit which is driven by a current source, which has 2 components in parallel, a resistance and an inductor, and the input current source is sinusoidal. 2 components are there, 100 cosine 10 cosine 100 pi t plus pi by 4 plus 20 sine 100 root 3 pi t minus pi by 6, and you are asked to find I L of t in its steady state, and it is also given that all initial conditions are 0. And the way to do question number 2 is you need to replace all components with their complex impedance form. Which means R is replaced by R, L is replaced by j omega L, C is replaced by 1 by j omega C. And remember, omega is the frequency of the input. Now, in this particular case, the input consists of two components. One component's frequency is 100 pi, the second component's frequency is 100 times root 3 times pi. So, what you need to do is you need to consider the circuit, replace R by itself and replace the inductor by j omega L, and then use current division property. So, this is I s, and you need to use the current division property and find the current in the inductor, and you need to do this for each input component. Namely, you need to do it for the first component with frequency 100 pi. You also need to do this for the second component with frequency 100 root 3 pi, and since the circuit is linear, the final answer is the addition of the answers that you get from each individual component. So, that is how you need to proceed with question number 2. Let us now move on to the next question. In the next question, you are asked to find the value of A naught minus A 1 by root 3 minus B 1 minus A 2 minus B 2 by root 3, and you are given a signal x of t which is 3 plus 2 cos omega t minus pi by 6 plus 2 cos 2 omega t minus pi by 3, and this is a periodic signal, and this is expressed in the Fourier in the form of a Fourier series. In particular, it is expressed in the trigonometric form, and you need to find the value of this expression, which means you need to first express the given signal x of t in the trigonometric form as given here. So, this question involves taking cosine A plus B and writing it as cos A cos B minus sin A sin B. Once you do this for each of these terms and then collect all the similar terms together, you will get an answer or you will get an expression that is in the standard trigonometric forms. Identify all the coefficients A0, A1, A2, B1 and B2, and then use those values in the expression given there and simplify. Now, let us move on to the next question. So, this is question number 4, right. By the way, these things evaluating the Fourier series is covered in unit 11, week 3, Fourier series lecture 2, and evaluating Fourier series coefficients is the title of the lecture. If you listen to that, you will be able to follow the questions and understand the questions we are doing right now and solve them. Now, let us look at question number 4. 4 and 5, these are very similar. You are asked to evaluate integrals of the form 0 to t sin m pi t sin n pi t dt, and for the fifth question, instead of sin for the second term, you have cosine n pi t, and this is pretty simple to evaluate these two integrals, and the steps that you need are, you need to know how to express sin A sin B for the first question, and then that is when I said for the fourth question, and you need to know the value of sin A cos B, and sin A sin B is half cos difference minus cos sum, and sin A cos B is half of sin sum plus sin difference. Use these two formulas and then break this single term inside the integral into sum of two terms, and then evaluate the integral and simplify, you will get the answers to questions 4 and 5. They are very similar. Let us now go to question 6. Question 6, you are asked to find the DC term A naught in the Fourier series expansion of the waveform given, which is a square pulse. Its amplitude A between 0 to T naught by 2, and from T naught by 2 to T the amplitude is 0, and this basic fundamental period repeats itself every T naught seconds, and you are asked to find the Fourier series coefficient A naught. And as you recall from the lecture, the formula for A naught is given by 1 over T 0 to T x of t dt. So, apply this definition to the function that is given there, and the integral is very simple and you will get the answer immediately. So, this is calculating the DC coefficient or DC value of this periodic signal given in question 6. Let us now move on to question number 7. You are given a waveform with half wave symmetry, and as you know, half wave symmetry is a function that satisfies f of t plus t naught by 2 equals minus f of t, and we are asked which of the following is / r true. So, you need to pick all the choices that apply, and this is discussed in unit 11 week 3 Fourier series lecture 2, and the title of the lecture is symmetry conditions. There Professor V.G.K. Murthy talks about what are the implication in terms of Fourier series components present in a signal that satisfies half wave symmetry. And if you follow the lecture carefully, the answers to this question, all the properties satisfied by half wave symmetry are clearly mentioned there, and you should pick up all the terms that apply for the general half wave symmetry. So, question number 7, f of t plus t naught by 2 equals minus f of t. So, this is half wave symmetry, and you need to look up the properties of harmonics, or rather the properties of the Fourier series expansion. Satisfied by half wave symmetric waveforms. So, this is pretty straightforward here. Listen to the lecture and you will be able to identify which are the properties that apply and you can choose the right ones. Questions 8 and 9 relate to symmetry of waveforms. Question 8 talks about which of the following functions given are even symmetric, and the question 8 is same set of waveforms, you need to find out which ones are odd symmetric, and even symmetry by definition is a function x of t satisfying x of minus t. So, look at the 4 waveforms given, find out which of the waveforms satisfy x of t equals x of minus t. For example, x of 1 should be equal to x of minus 1, or x of t naught should be equal to x of minus t naught for all t naught, right. So, that is easy to identify, and the pictorial interpretation of x of t equals x of minus t, that is a function satisfying even symmetry, is basically you take the function, reflect it about the y axis. So, if the negative time portion is a reflection around the y axis of the positive time signal, then the signal is even symmetric. So, this should be easy to identify by looking at all the waveforms. And question number 9, you are asked to identify odd symmetry. Odd symmetry is x of minus t is minus x of t. Again, the pictorial interpretation of this is if you reflect about the y axis and the reflection is negative of the positive portions of the signal, then the signal is odd symmetric around the origin. So, that is the mathematical way of stating that is x of minus t equals minus x of t. Again, look at all the waveforms that are given, find out which ones appear to be the negative portion must be not only reflected, but also sign change. So, this is odd symmetry. Moving on to the next question, this is question number 10. You are given a general signal say f of t, and then you are asked to find the even and odd symmetric parts. In this particular case, the signal f of t is e to the j t. Now, again this is a question of applying the basic definition here, right. So, any signal x of t can be written as a sum of x e of t plus and x odd of t, that is x e of t is its even part, x o of t is its odd part. X e of t is nothing but x of t plus x of minus t by 2, right, and you can immediately see that x e of t equals x e of minus t. Therefore, this is even part, and x o of t, which is the odd part of x of t, is nothing but x of t minus x of minus t by 2, and you can immediately see that x o of minus t is minus x o of t. So, this indeed is even symmetric, the even part, x o of t is indeed odd symmetric, and if you add these two, you should get back x of t. Again, it is easy to verify that x of t is indeed x of t plus x of minus t by 2, which is the even part, plus x of t minus x of minus t by 2. This is the odd part, and if you simplify you get back x of t, and we saw that the individual components are the even and odd parts respectively. And take e power j t, write this as cosine plus j sine, and then find the simplified value of x of t plus x of minus t by 2, that should give you the even part, and x O of t should be x of t minus x of minus t by 2, that should give you the odd part. One remark I would like to make in this context is you should know the difference between the even part and conjugate even part. Okay. So, this is a new definition. Suppose the signal, do you want to check whether it is conjugate even? What is the definition of conjugate even? Conjugate even means x of t is x star of minus t. So, compare this with the earlier definition of even. A signal is said to be even if x of t equals x of minus t. So, that was even, but conjugate even is if x of t equals x star of minus t, then it is conjugate even. Similarly, if a signal x of t equals minus x star of minus t, then it is said to be conjugate odd. So, these are two different definitions, and typically we apply the conjugate even definitions to complex signals and the earlier given definitions to real valued signals, but it is not the case that conjugate even and conjugate odd apply only to complex signals. Both even and odd and conjugate even and conjugate odd can be applied to either real signals or complex signals. Now, as an exercise, take the same signal f of t equals e power j t, and then write this as a sum of conjugate even plus conjugate odd. Express it as its conjugate even part and find the conjugate odd part of e power j t, and notice the difference between expressing it as even plus odd part. So, this conjugate even and conjugate odd part is not part of the assignment, it is a concept that you need to know, and these are the definitions, and apply these definitions to the same example that is given, and notice carefully the difference between decomposing it into its real and even and odd parts versus conjugate even and conjugate odd parts. Now, as you might have seen in the lectures, even and odd symmetry signals, their Fourier series expansions satisfy certain properties. That is, if you have an even signal, its Fourier series coefficients satisfy certain properties. If a signal is odd, again some other property is satisfied, and the properties of even and odd signals, that property is tested in question number 11. So, in question 11 we are asked which of the following signals has only sine terms in the Fourier series expansion, and you are given various choices and you need to pick up all the choices that apply, and what you need to recall from the lecture, if the signal is even, then the BK terms are absent. Recall, BK terms are the coefficients of the sine terms in the trigonometric expansion. Similarly, if the signal is odd, then the AK terms are absent. And recall, AK terms are the terms A naught, which is the DC term, and A1 through infinity, which are the terms corresponding to the cosine in the trigonometric expansion. Therefore, question number 11, which tells you which of the following signal has only sine terms, it is another way of saying check for any symmetry that the signal might have. Does the signal have odd symmetry? If it does, then it has only sine terms. So, this is what you need to do for question number 11. Let us now move on to question 12. Which of the following signal has only odd harmonics in the Fourier series expansion? So, this is another kind of symmetry that a signal might possess that has implications on what kind of harmonics are present. In this particular case, you need to check for half wave symmetry. Check for half wave symmetry. So, this is discussed in unit 12 week 3 Fourier series lecture 3. The title of the lecture is symmetry condition examples. So, you need to check for half wave symmetry, and if f of t equals minus f of t plus t by 2, then only odd harmonics are present. Therefore, the question which of the signals has only odd harmonics in the Fourier series expansion is another way of stating check for half wave symmetry. If the signal has half wave symmetry, then it will have only odd harmonics in the Fourier series. Thirteenth question again relates to half wave symmetry, except that this half wave symmetry is even symmetry, and check for the property that is satisfied in such a case. As mentioned in the video lectures, one way of looking at this is thinking about the Fourier series being periodic with period t by 2. However, it is also useful to think of this as being periodic with period t and then seeing what harmonics are present. For example, if you consider a simple sine wave and if you rectify it, you will get a signal that satisfies this property provided the rectification is full wave. in such a case you will find that if you want to analyze this signal based on its harmonic content, but you want to relate this with respect to the original signal, it is useful to think of the period to be still t and then think of the full wave rectified signal as being having half wave even symmetry. Let us move on to question number 14. In question number 14, what you are given is a partial waveform of a periodic signal. The period is t naught and you are given information from 0 to t naught by 4, and you are also given the fact that the full waveform has only odd harmonic sine terms in its Fourier series expansion, and then you are asked which of the following could represent the full waveform. That is, the Fourier series expansion has only odd harmonics and not only that, only sine terms are present. So, what this says is if only sine terms are present, it has to be an odd symmetric sequence. If only odd harmonics are present, it must satisfy half wave symmetry. So, combine these two facts and then complete the waveform and choose the one that, or choose not only one, I mean as many waveforms that satisfy this condition. Moving on to the last question, you need to refer to unit 12 week 3 Fourier series lecture 3, and this is right at the beginning of the lecture titled Applications to Network Analysis. What you are given here is you are given here a waveform that is periodic with period t naught, and then as you know this can be represented in terms of a Fourier series, and what you are asked in this particular question is you need to find the value of a plus b, where a is the term multiplying 1 over pi and b is the term in which is the coefficient of sine 100 pi t. This is very similar to the problem that has been worked out in Professor V.G. K. Murthy's lectures right at the very beginning. If you watch that, this is a very minor variant of that question. You should easily be able to find what the value of a plus b is. So, this concludes this short video on hints about solving the assignment that is due next week. So, please look at all the problems carefully, work them out. They are not very difficult, but they very nicely capture all the concepts that have been explained in the video lectures. Thank you.